All right, so in this video lesson, let's look at an example of how we can apply integration by parts to solve an integral, an indefinite integral. And this is an example as an additional example aside from those examples I have already delivered in the general lecture about the integration by parts technique. Okay, and so this video lesson here, this example is intended to be viewed after you have watched my general video lecture about the integration by parts technique. And along the way, as well as somewhere near the end, I will be able to explain what's special about this particular example right there. Okay, and so let's get to the example itself. And so here in this example, we are looking at evaluating the following indefinite integral. So it's the integral of e to the x cosine of x. Okay, and so the function that we're attempting to find, the indefinite integral, has, it is in a form of a product of two separate functions. There's an e to the x in product with cosine of x, and then of course multiply with dx. And so as I said earlier, this lesson here, this video example here, should be viewed after you have already seen my general video lecture about the integration by parts. So I brought in the Liate guideline in my general lecture there. And so here we are going to see how this problem is still being aligned with the Liate guideline right here. So in the way how I see it, with our understanding already of the Liate guideline right here, then this e to the x is one member in the exponentials or the exponential functions. And so this is e, that's to be from this Liate guideline right here. And then cosine of x is one of those members of the trig functions. Okay? And so now, according to the Liate guideline, then the function in the trig family has higher priority that gets to be chosen as a u choice. And so in that way, now I have a clear indication of which u choice should be a good one to start out first. Okay? And so now I am going to start out u to equal, I'm going to set or substitute u for cosine of x. Okay? And so that means du dx equals negative sine of x. And so we have seen this many times enough in my general video lecture about integration by parts. We can multiply the differential dx on both sides. That produces du equals minus sine of x dx for us. Okay? And then on the other hand, and let's now set that that original problem aside right here. So I'm handling the by parts. Okay, so this is the part that we made the u choice. And so once we've made the u choice, then everything else back in this original expression here, including the dx. So just like the way how I explained that back in the general video lecture on integration by parts. And so everything else, meaning there's e to the x left over, and then there's in product with dx. All of that here now is going to be expressed as a dv differential, or being recognized as a dv differential. So now, clearly speaking, this integral of ours right here is in the form of a u dv. Okay, but now back to what I was in the middle of doing. Now we can find v here by simply integrating or check the indefinite integral of e to the x. Okay, and so that's why now v equals e to the x. And just like how I explained back in the general lecture, then we can, for this small step right here, then we can skip the plus c. Okay, and so now we are ready to apply the integration by parts formula. And so the integration by parts formula again has the formula as following. As long as we can recognize at any time that we can recognize our integral to be in the form of a u dv, then the formula says we can multiply u with v after we recognize them, and then subtract an extra integral v du. Okay, and so, of course, our starting problem is here. E to the x cosine of x dx, and all that all that u dv is here. U and all these two as a product, dv. And then, so according to the integration by part formula, then u times v. So again, recall for ourselves, u is cosine and v is e to the x. And so u times v gives me, according to the formula, u times v equals, and algebraically we should express that as e to the x times cosine of x. Okay, and then now we are going to subtract an extra integral that we are going to produce. And so this integral v du. So v in the parts that we split it down right here, then v is e to the x, okay, and du is minus sine of x dx. Okay, and so let's put the pieces together here. So it becomes a minus e to the x sine of x dx. So all that here is v is just the e to the x, but we have to put the negative sign in front because minus sine of x dx. That's why, that's what consequented in that minus sign right there. And so that means we can now allow me to do this the dirty trick right here a little bit, but I mean it's not dirty trick, but it's just a little bit illegal that I have to, because I'm trying to save space here, so I'm going to quickly erase that minus sign because they're going to cancel out and become plus sign. Okay, so it means that in the next step it should be a plus the integral of this e to the x times sine of x. Okay, so in some of my short videos showing different examples, then I believe I've had a different videos where I pointed out that when you are applying integration by parts, then there will be times where you have to apply integration by parts more than once, and it could be 2 times or it could even be 3 times. It happens here again in this problem. So it looks like we're running into another, so this first term is done, but that term here requires a second step or a second time of taking the integration by parts. And so let's observe that clearly, closely, because I'm going to swing back to the other board and then I'm going to once again split out the part, right? There's a u and there's a dv again. Now, in some of my other video examples, and I after using u and dv, I also try to use s and dt, but here I'll just stay with another u and dv. But you gotta be aware that it's a different u and dv pair now. Okay, it's not the same u and dv pair anymore. All right, so Liate scheme Liate guidance is still here. I can see this is exponential and this is trig. Okay, and so now back on my original board. Again, I'm now going to erase this because we're going to do the next step, the second step, u and dv. And so in that way, I have to erase all this. The original problem is here. We're on our way for that, but now we are trying to find the by parts, the parting step of u and dv is here. Okay, and so now my u is chosen in this Liate guideline. U is chosen now to be sine of x. Okay, and so that means du dx equals cosine of x, and that consequently leads to du equals cosine of x dx. And you have seen this logical argument so many times throughout the lecture, so allow me to skip the explanation here again. And so now at that instance where we chose this u substitution, this u choice for our integral right here, okay, then again, just like how I explained back in the integration by parts. So anytime you're carrying out the integration by parts, then you have to always stay, if your problem stays with if your problem, as long as you're still working with the integration by parts and stay with that, once you make your u choice, then everything else, including the d expression there, has to be the dv. Okay, so our u choice was here, was the sine of x. So e times dx will consequently be all of that, all of yours dv right there. So now back in my other board right here. So dv, and again, this is not for that problem right here. It's just for the other problem on the other board. So dv equal, let's see what I have here, e to the x dx. So that's my dv. So to find v from here, I can go taking the integral, the indefinite integral of e to the x dx, and that again gives me e to the x. And just like how I explained in the general lecture, then we can skip the plus c for this small little work right here. And now let's put the pieces together in my other board. So in the next step, okay, we have that first term here remains the same, nothing much to be done, e to the x times cosine of x plus, now I'm going to open parentheses. So now we are going to write down the integration by parts formula specifically for this, and we're going to put everything there in the parentheses. And that's what my parentheses is here for. Okay, and so it is now this integral, see, u and dv. So your u was the sine of x. So now, and times with v equal being e to the x. Let me u and v, okay, u times v. And so now we're looking at e to the x times sine of x. Okay, but now I'm going to need to subtract according to the integration by parts formula. So we are going to subtract an additional formula, an additional integral over here, and now that brings in v du. But our most recent step of the v du, okay, not the very first v du pair right there. Okay, so now v du, again, remind for yourself, v is here e to the x, but du is a cosine of x dx. Okay, and so in that way, minus e to the x times a cosine of x dx. And we can remove the parentheses. So allow me to do that illegal step again, because before this parentheses it was a plus sign, so removing the parentheses will not change. But now I have a closer look. It looks like we're not going anywhere. So we got the first term here from the earlier work, and then we applied the integration by parts for the second step, and we got this. But then looking at this thing right here, it's starting to get a little scary in a sense that this is exactly the beginning problem. So it looks like we are looping around, we're not going any further. So some of you viewing along with this video lesson might think, hey, why don't we apply the integration by parts the third time? But I can see it's not going anywhere because this is exactly the beginning point. Okay, so here's the thing. Here's how algebra has always been a good usefulness for us. Okay, so if you have learned with me for differential calculus, and now you have learned throughout the quarter with me here, I will constantly remind you, you got to get your algebra going, and the stronger your algebra is, the bigger that bonus is for yourself. Okay, so anytime that you can carry a big algebra or a big solid algebra skill with you right there, then you have a bigger bonus when you're doing any of these calculus work. The point now is that this is our starting problem, and it's supposed to equal, it equals this, and our original problem equals that. Okay, and so here, allow me to do this. I'm going to take this beginning problem, and I'm going to put it here. Okay, because they're equal. The beginning problem equals this middle step and also equal this current step. And so we have our algebraic right to set these equal. I said algebraic rights, okay? And so integral of e to the x cosine of x dx, our original problem should equal this. And so now I want viewers, I want students of mine to see this as an equality. If you are now starting to, forget about solving integral. Forget about solving the integral right now, but simply treat this as an equality, as an equation. Okay, then what do you see? We have this term, and there's the exact term on the opposite side. And that means now I can bring that term it has a subtraction sign right here. I'm going to add this term to the opposite side, okay? And my word here, I'm adding this term to the opposite side, okay? And my observation was that this term is the exact term of that, but on the opposite side it has the negative sign right here. So I'm adding that term to that left side. So now I quickly stepped out to grab a red marker, but now I'm going to add to emphasize that idea right here. And this is a really good trick that, once you pick this up, it's going to be quite useful here and there sometimes. And it's a quite famous special problem as well. And then it's special in the way how it is. E to the x, I'm going to add e to the x cosine of x dx. See, I'm adding this expression. I'm adding instead of subtracting. So adding that from both sides, because again, I told everyone that see this as an equation. So you can always algebraically add one expression to both sides. So if we added that red one, then we also add this. Integral of e to the x cosine of x dx. Because, we believe that this integral has it is an expression, it has some answer. It's just right now, we're running into a loophole. We keep looping it around. And so, but knowing it will have some answers, so we can just simply add that expression to both sides. It's an expression. You can always add an expression to both sides of an equation. And so this is what consequently turned out right here. All right, so in the next step, I'm going to have to write it at the lower side of the board. On the left-hand side, these two are identical terms being added. Okay, and so that means I'm producing 2 times of the expression integral of e to the x cosine of x dx. Okay, that's the left-hand side. And the right-hand side, of course, these are canceled. Okay, and so everything remains on my right-hand side are these 2 terms right here. So e to the x cosine of x plus e to the x times sine of x. We are very close. Some viewers may recognize where to go next already, but I will get there as well. Okay, so have a good look at this. Right now I have the integral here, but 2 times of this integral equals all that. Okay, and so now in my other board, allow me to erase this. And allow me to again copy down the very last line we've had from the other board. Okay, and I'm still leaving the original problem here. So the very last line what we had from the other board was 2 times the integral of e to the x, okay, cosine of x dx equals e to the x cosine of x plus e to the x sine of x. Okay, but now seeing this as an equation, again, seeing this as an equation, so where did you learn all of this? It's all the algebra that runs behind the scene right there. So there's always a good reason that I remind any of my students, get your algebra going. Every little skill of yours will contribute in doing your calculus work. Okay, and so now what's the next algebra move that I can do here? Divide both sides by 2. Divide both sides by 2. And so I'm going to divide both sides in red ink to especially catch your attention. Divide both sides by 2. So look at what I have ended up for myself. Left-hand side now remains just simply that expression, the integral of e to the x. What it says, what it reads now, the integral of e to the x cosine of x. Okay? And that left-hand side expression, one single term, right? Coefficient 1. And now all of a sudden we found out that equals e to the x cosine of x plus e to the x sine of x, all of that over 2. What have we done here? We have found the final answer. That was our original problem, and we would like to find the answer to that. That's what we have found. This is the final answer, the indefinite integral of e to the x cosine of x. So at some point it was looping around. At some point we applied the integration by part step twice, and then at some point we ended up with that beginning point. But then, now thankfully with some algebra, we added it. It's a famous trick and hint now, whatever you want to call it, but we add that exact term to both sides, and we produce this. So on the left-hand side here, we had 2 times of that, whatever that is, and then, so algebraically, again, I divided that coefficient 2 away from both sides. Look at what I ended up. Okay, but wait a minute, there's still a little more. Don't forget, plus c, okay? Because sometimes we get too excited that we found something fabulous, and then we tend to forget some of the core requirements one. Plus c, because this is our final answer to an antiderivative problem, our final answer to an indefinite integral problem. But now, ladies and gentlemen, you have found the integral to e to the x cosine of x dx. Okay, so this example itself is special in a sense that the way we approached it requires us to bring in some surprising algebra trick that, you know, back in the days we study algebra, it's adding an expression to both sides of an equation. We speak that so easily, we say it so easily, but this is where we can creatively use that simple trick and it gets the problem done. Okay, and so that's what makes it special about, and the problem itself on its own is special. Okay, and now here, as I say, this is our final answer to this antiderivative, to this the final answer to this indefinite integral problem. Before I completely close down the integral, I mean the example, go ahead and take the derivative of this to convince yourself that this is the correct answer that we have landed into.